I want to welcome you to the Helicopter Owner's Indoctrination course. This course was specially prepared by Rotorway to fulfill three needs. If you're considering buying a Scorpion, it will help you to evaluate your purchase. If you're preparing to build a Scorpion, it will provide valuable assistance in the construction of your craft. In fact, Rotorway feels that proper training is so vital to the successful operation of any technical project that this course is a mandatory prerequisite for the Scorpion builder. Thirdly, it will help you to expand your horizons of knowledge about helicopters, whether you're considering building a Scorpion or you just wish to learn more about what makes a helicopter work. I'd like to take you through a tour of the Rotorway facilities. Just prior to 1970, Rotorway was located in a building about the size of the tan building in the center of the photo, the second from your left. We've been expanding ever since. In fact, since this picture was taken, another building has been added just to the rear of that building. It now occupies the space where you see the two yellow trailers and the old helipad. The building in the left foreground is Rotorway's foundry. This is the only automated sand handling foundry in the state of Arizona and is known nationwide as one of the most precision foundries in the business. The tan building to the right is the offices and the pattern shop for the foundry. To the right of this building is the piston-powered products division, where we make the piston-powered saw, the drill, and the grass hog. The large building to the right is the main helicopter factory, and this is where the components for the helicopter are manufactured. In the background, you'll see a building which is under construction. This building is now completed and is the fabulous new Scorpion Sky Center, our new sales and training center. As you enter the lobby of the main building, you meet our receptionist and telephone operator. That's the pleasant voice that answers the phone when you call in. To the right, you'll see some of the trophies that the Scorpion has won. Let's go through the door in the rear, through the office complex, and on into the main plant. This is where the helicopter starts in the tube bending area. The Scorpion airframe is made of 4130 chromoly steel. This is a special aircraft steel. It's very strong yet lightweight. It takes special bending techniques to bend 4130 to keep it from collapsing or from kinking. We've developed this special hydraulic bender which bends it to the precise shapes required. After the metal is bent into the proper shape, it is then taken over to the jig area. In this fixture, the airframe is jig fitted and tack welded, so when you receive your airframe, it'll already be properly aligned, and all you'll need to do is finish the welds. In the background, you can see some of the airframes that are already finished and are ready for shipment. This is an interior view of our modern foundry. Several years ago, we decided to go to castings in many areas of the Scorpion to make it more professional and to keep the cost down. But we had a problem finding a foundry that could cast to the precision that we desired. Therefore, we decided to build our own foundry. In the left center, you'll see the fires of the furnaces. In this foundry, we pour non-ferrous materials, primarily aluminum alloys and brass. In the right foreground, and extending back through the center of the picture, you'll see a grill work in the floor. This houses the underground conveyor belt which handles the sand. In most foundries, the sand is handled from station to station with shovels and wheelbarrows. Here, the only shovels and wheelbarrows you'll see are used for cleanup at the end of the day. The sand starts in the large yellow hopper at the rear of the building. There it is filtered and cleaned, and then it is transferred to the orange hopper to the right, which is a muller machine. Here the sand is reconstituted with chemicals and moistures for the right consistency, and then it goes up the conveyor belt to the overhead distribution system on your right. From here it is dropped down through automatic hoppers down to the molding stations where the molders make the molds. The molders then put the molds on the conveyor tracks, they move over to the left, and the metal is poured into the molds. After the metal is cooled, the molds are broken open, the parts removed, and the sand goes back down through the grill work to the underground conveyor belt and back to the yellow hopper for reprocessing. It is this foundry, with all the capability it gives us, that makes the Scorpion so feasible. It's also what made possible the development of our own power plant. The Scorpion is the only general aviation aircraft with its own power plant. In our extensive machine shop, the parts from the foundry and other raw material purchased from the outside is precision machined for you. Those of you that are familiar with machine shops will recognize the large Warner Swayze lathe here. You'll also see in the background Bridgeport mills, other lathes and machines used to make these parts. So you'll not need any equipment such as this to make your helicopter. All of the heavy and precision machining is done for you. This is a view of our fiberglass department. Most fiberglass today is made by a chopper gun. The chopper gun is a much faster and more economical means. However, it is not as strong and is very heavy. Because in an aircraft we're interested in lightweight and strength, we use the hand layup process. In this area, the cabins, seats, instrument panel, oil bath, and all the other fiberglass components in the Scorpion are made, right here in-house. This is a view of our blade area. The blade is the heart of any helicopter. The design and construction of a helicopter blade is extremely critical. Not only must they be aerodynamically equal, but they must have the same physical properties such as weight, rigidity, and resonant frequency. The blades for the larger commercial helicopters start at around $6,000 to $9,000 a set, yet in the Scorpion we can make them for a fraction of that price. Our technology in this area is another one of the things that makes the Scorpion so practical for the average person. As I mentioned earlier, Rotorway makes its own engine. For those of you who have followed the Scorpion for a number of years, you'll recall that we used to use the Evinrude outboard motor. When Rotorway started to develop the Scorpion helicopter, the selection of an engine was given prime consideration. Many engines were looked into. One of the first and most obvious engines to look into would be the standard aircraft engine. But you see, aircraft engines are designed to run horizontally with a prop out front. It doesn't run well vertically. We wanted a vertically running engine so that we wouldn't need a gearbox to transfer the direction from horizontal to vertical, because the gearbox or transmission in a helicopter would be as expensive as the Scorpion itself. Now you may say, I see larger helicopters that have the engines running vertically. Yes, they do, but you see, during the war when the military wanted helicopters, they paid for the development of vertical running engines. This was a very costly process, but the engines they developed were large engines for large helicopters. They're too large for the Scorpion, and all of the other existing aircraft engines in the smaller category are not suitable for running vertically. We investigated many engines: the Continental, Lycoming, Franklin, Chevrolet, Porsche, Volkswagen, many foreign engines such as the Wankel, the NSU, the Mazda, you name it. We've probably tried it. And yet we found that the only engine that made the Scorpion possible was the Evinrude outboard motor. The Evinrude was a fine engine, but it was a two-stroke engine which required the mixing of the oil and the gas, and this, as you're aware, causes spark plug fouling. The Evinrude was also a V4 configuration, and a V configuration engine has a rocking couple moment of vibration. Also, two-stroke engines have to run at a very high RPM, and they don't develop very much torque. We wanted a four-stroke engine for the Scorpion, but none was available that was suitable for our application, and thus it was we decided to develop our own engine. We have designed, developed, and are now producing the RW133, a horizontally opposed, four-cylinder, four-stroke aircraft type engine. All right here at Rotorway for the Scorpion. This engine is water-cooled. You see, in a helicopter, in a hover, it requires almost maximum horsepower, and at that time there's no ram air. In your car or in an airplane, when you're developing maximum horsepower at maximum speed, you have ram air. To have an air-cooled engine would require a tremendous blower. If we were to use an air-cooled engine, it would require about 36 horsepower of blower to cool it in a hover. But because of the greater coefficient of cooling of water, we can cool this engine with about 6 horsepower. Another advantage of water-cooled engines is that they run quieter because they have a water jacket around the cylinders, and you don't have all those air fins which radiate sound. A water-cooled engine runs cooler than an air-cooled engine, and therefore you don't have as much exhaust emissions. Another distinct advantage of water-cooled engines is that we can make the pistons smaller and therefore get by with a single ignition system. Those of you that are aware of aircraft engines realize they have dual ignition, and many people think that this is for reliability, but this is not the case. You see, in an aircraft engine, because it is air-cooled, it has to be much larger, and because it's much larger, the pistons become very large. Since the pistons are large, it requires 2 spark plugs to fire this total wavefront of gas. Now, this will be evidenced by those of you who fly fixed-wing airplanes. You know that when you pull a mag check, you get a power drop. Why do you get a power drop? Because you're not igniting all the fuel. If you can make the piston smaller in diameter, then 1 spark plug can fire the entire wavefront of gas. So with a single ignition system, we have only half the number of ignition parts to go wrong, or we can say we have twice the reliability. In this slide, you'll see the engine being installed into the dyno. Every engine is put into the dyno and pre-run, tested, timed, and tuned. You'll receive your engine ready to run. This is a view of our packaging and shipping department. Here the components are carefully inventoried and packaged in specially prepared cartons. Here careful control is maintained over the customer's records, so we know exactly how many parts were shipped, in how many boxes, the total weight, the day they were shipped, and the truck line by which they went. Here is a picture of the completed fabulous Sky Center which you saw under construction in the first photo. In the Sky Center are housed the executive offices, the sales offices, and the training center. It is this training center that makes the Scorpion so unique in this field. As you enter the lobby of our Sky Center, you'll meet our friendly receptionist who will sign you up for your schooling if you're here for training, or make an appointment for a salesman if you're here to see the Scorpion helicopter. You'll then be ushered into our spacious lounge. We feel that we have a quality product in the Scorpion, and when you're here visiting with us, we wanted you to have quality surroundings, so we've designed this lounge with you in mind. You can sit in the comfortable chairs and watch out the floor-to-ceiling glass windows out on the helipad area and watch the helicopters practicing. Over to the left is a fireplace with a conversation pit where you can sit around and talk with other friends. In the background, you notice a spiral staircase that goes up to the top side. There's an observation deck and a rooftop heliport. We also have a snack bar here for sandwiches and coffee. Let's go on around behind the wall in the rear with the wrought iron grill work and go to the classroom area. Here we have large, spacious area and modern classrooms. You notice in our classes that the wives are there too. We encourage that you bring your wife with you. She should be a part of your project. Here you will see a class in session on the pre-construction tips for the Scorpion helicopter. It was from this schooling and these classes that we developed the concept for the Helicopter Owner's Indoctrination course. Now let's go on back to the rear of the building. We come to the bay area. This is where the ships that are used in the school are hangared, serviced, and maintained. My, don't they look pretty? Next, we're going to discuss some of the philosophy of the amateur or custom-built category under which the Scorpion is licensed. While you're studying this Helicopter Owner's Indoctrination course, we want you to do some evaluating. First, we want you to evaluate us. What is the Scorpion? What is the quality of its construction? Will it do for you what you want it to do? What about the Rotorway facilities? Do we have the facilities and capability to design and build a product like this? Will we be here 5, 10 years from now when you need replacement parts? And what about the Rotorway program? Do we have a program that will make you successful? These are the things that you need to evaluate. At the same time, we want you to evaluate yourself. As you go through this course, you'll see the skills and equipment and time involved in undertaking and building your own helicopter. Evaluate yourself. First, do you have the ability to build it? We don't want to sell the Scorpion to someone who is not capable of building it. You should have at least average mechanical ability. You should be able to change a spark plug in your car, fix a bicycle. It'd be helpful if you've built some project before, such as a model airplane or a dune buggy. If you do your work in your own car, can you repair a leaky faucet around the house? These are some of the things that will help you to see if you have the ability. Next, evaluate your aptitude. Maybe you haven't much experience in mechanical work before, but maybe you have the aptitude for it. As you watch the slides coming up, you'll see what's required in the building of the Scorpion, and see if you have the aptitude to do this. And lastly, but perhaps most important, is your attitude. What is your attitude towards this project? Are you willing to follow the instructions, take advice, build it the way it was designed, or do you think you know more than anyone else? Do you think you can improve the design? Do you think you don't need instructions? We only want successful customers, and we have a program to make you successful. But to be successful, you must be willing to follow the program. Let's take a look at the cost of helicopters. People oftentimes ask, why don't you certify the Scorpion helicopter? Why don't you make it a turnkey operation? Just sell me the key, I'll put it in the ignition, turn it on, and fly away. Well, let's look at some of the cost involved. First, if we took the basic cost of the components and constructed them ourselves here, the helicopter itself would have to sell for about $20,000. To this, we would have to add certification cost. Certification is a process that Rotorway would have to go through to get an FAA type certificate. This is an extremely expensive process. It requires years of testing, reports, forms, analysis. And when we got this type certificate, it would be for that particular design. No changes could be made without recertification. So we would have to figure how many ships would we sell before technology would advance, improvements would come along, and we'd make changes which would require recertification. We divide this number of ships into the total cost, and we see we have to add about $10,000 to the cost of each helicopter for certification cost. Then there's the matter of insurance. If we sold a completely certified, ready-to-fly helicopter, we'd have to carry product liability insurance. Product liability insurance on a helicopter of this size would run about $10,000 premium per aircraft. Now, this is not liability insurance that would insure you if you injured someone or you had an accident. This is only insurance to protect us from you if you had a problem. Look at what that does to the cost of the aircraft. Yet, in this custom-built category, when you get it licensed by the FAA will specify you as the manufacturer of the aircraft, relieving us of the liability problem. We sometimes sort of laughingly say, if you don't like the way it was built, then sue the manufacturer. You're the manufacturer. After all, why should you pay insurance premiums for someone less careful than yourself? And then we have dealer cost. If we're going to have a turnkey operation, we would have to have maintenance and service stations all throughout the United States. You see, one of the advantages of the custom-built category is that you can do your own maintenance. In a certified aircraft, it must be done by a certified A&P mechanic. So we'd have to add about $10,000 per aircraft for the dealer. That would give him a 25% markup, which is reasonable. So you can see that we now have a $50,000 helicopter. Now, wouldn't you really rather do it yourself? In a certified helicopter, the cost of the aircraft does not include the flight instruction. This is extra. Let's take a look at what it would cost to get a helicopter license. Now, the FAA says that it takes a minimum of 45 hours to get your rating. However, most people find it takes closer to 60 hours. And if you've priced helicopter instruction around the country, you'll find that $100 an hour is a pretty fair price. In fact, in many areas, it's much more than that. So you take $100 an hour times 60 hours, and you're looking at $6,000 to learn to fly. Not only $6,000, but let's look at this. 60 hours. And the FAA recommends only an hour a day. You see, beyond that, the physiological and psychological excitement builds up, and you just can't learn much more than that. It's like skiing. You notice that all the ski accidents happen late in the day. A person skis all day long, and they're having such a wonderful time, why, they don't even realize how tired they are. Toward the end of the day, they try to get in that one more run before the ski slopes close, and they fall down and break a leg. It's hard to realize how tired you really are when you're having such a good time. All right, so we look at 60 hours, that means 60 days. And there's 20 working days in a month, so 60 days and 20 days a month, that's 3 months. And in many areas of the country, unless you live in a large metropolitan area, there's probably no helicopter schools close by. You may have to travel several hundred miles to get this training. In many cases, people have had to actually move and live in the area for 3 months while they're getting their schooling. Now, this just isn't practical for the average person, and this is another one of the reasons why the average public does not have a helicopter. In addition to all that, this schooling includes only learning to fly. It does not provide you with any ground schooling. By comparison, look at the Sky Center program. With the Scorpion, the flight training comes included in the price of the helicopter. You'll receive the required dual training in a Scorpion here at the Sky Center. You'll be endorsed for solo flight, and then you can go home and put in the balance of the 45 to 60 hours in your own Scorpion, at your own leisure, at a tremendous savings in price. And not only will you learn to fly your helicopter while you're here at the Sky Center, but you'll attend classroom instruction on theory, rigging, maintenance, and operation of your Scorpion, as well as receiving all the ground school training required for your written examination. Here you'll see a catalog that is familiar to many of you, the Heathkit Wish Book. If you wanted a color TV set and you decided to build an RCA color TV and went to RCA and bought the diagram and bought all the parts and took them home and put them together, what do you think the chances are that the set would work when you got through, provided you're not an electronics expert? Very slim, right? Yet you can buy a Heathkit color TV, put it together, and it'll work. Does this mean that Heathkit uses better resistors and transistors and parts than RCA? No. It means that Heathkit has a program to make you successful. And the same is true with the helicopter. If you wanted a Hughes 300, such as you see here, and you went down to Hughes, and you bought all the blueprints and all the parts for this helicopter, and then took them home and put them together according to the prints, again, the chances of it working successful would be very nil. Why? Because you're not a helicopter expert. Yet you can buy a Scorpion kit, put it together, as many before you have done, and be extremely successful. Does this mean that Rotorway uses better parts than Hughes? No. It means that Rotorway has a success-oriented program, and if you'll follow this program, you'll be successful. But we do have a problem. Our customers are very smart. Now, how do I know they're smart? Well, if you're thinking of making an investment like this in the Scorpion helicopter, you must have the money to do so. And if you have the money to do so, you must either have a successful business or a good job. And if you've got a successful business or a good job, it must mean that you're smart. And here's where our problem starts. Here you'll see one of our smart customers. He's trying to build an airplane, but something's wrong. He's scratching his head. He can't quite figure out what the problem is. It doesn't look quite right. Now to you and I, we see what the problem is. On the corner of the table is a crumpled up piece of paper that says, instructions. Now, how come those instructions are all wadded up like that? Why isn't this fellow reading those instructions? It'd solve his problems. But you see, he's a smart customer. He's intelligent. He knows he's intelligent. And he knows that those instructions were meant for people less intelligent than himself. Anyone can build a model airplane. You don't need those simple instructions. But my goodness, look at the problems this gets us into. Let's do a little exercise. Go get a pencil and paper. First, write down the number of days in a normal year. Not leap year, but a normal year. Now, write down the number of weeks in a year. And lastly, write down the number of days in a week. Now let's see what you wrote down. Unless you're using some sort of a space calendar or something, you probably wrote down 365 days in a year, 52 weeks in a year, and 7 days in a week. These are figures that everyone is familiar with. Now I want you to multiply the 7 days times the 52 weeks. What did you get? 364 days. The numbers don't add up, do they? Now you're a smart customer. What's the problem? You see, there's not 52 weeks in a year. Look at your calendar very closely and you'll see that there are 52 weeks plus 1 day in every year. That's why Christmas falls a day later every year. You see, in all of our smartness, we get ourselves into problems. We think we know all the answers, but many times there's little hidden things that we've overlooked. So the secret is, don't assume that you know the answers. Read the instructions, all the instructions. Read them completely, study them. Make sure you're doing it right. Let's take a look at the certified category of aircraft. We see that the certified helicopter is built on a certified assembly line, a line that has the tools, the fixtures, the jigs that are required to make this aircraft according to FAA certifications by certified workers, workers who have been trained and have taken tests and have been certified and qualified to build those particular areas they're working on. And not only do we have certified workers, but we have certified inspectors inspecting the work that these certified workers did, making sure that the work was done properly. And when the helicopter is finished, it's then turned over to a certified test pilot who works full-time every day doing nothing but testing that particular make and model of helicopter. He knows it inside out. He knows what to look for. It still will take the certified pilot from 4 to 20 hours to test the ship out and make sure that everything is operating properly and all the adjustments are correct, even after all these certified workers have worked on it and the certified inspectors have inspected it. And then when the helicopter is all completed and ready for delivery, it'll usually be sold to either the military, the government, or some large commercial operator who can afford to have this commercial ship. Since helicopters are so expensive, they're not flown by novices, but they're flown by highly qualified, generally commercial pilots. And when this helicopter needs some repair, it'll be repaired and maintained by a certified A&P mechanic. Now let's look at the Scorpion. Where is it being built? Where is that certified assembly line? Probably your garage. Who's that certified worker that's going to be building it? It's going to be you. And who's going to be inspecting this work? You are. Maybe you get your wife to help. And who's going to test fly this craft when it's all built? Who's going to be the test pilot? Yes, you guessed it. You are. And who's going to be the pilot that flies it? Yes, again, it's you. And who's going to be the mechanic to maintain it? Yes, you. Now I ask you, who has the problem? That certified helicopter or the Scorpion helicopter? You see, we have to train you to become the equivalent of all these things. A certified worker, a certified inspector, a test pilot, the pilot of the craft, and the mechanic to take care of it. We have a program to do this, but you must follow the program if you're going to be successful. You see, this is the day of instamatics. We have instant pictures, we have instant coffee, you can even get instant diplomas. Think for a minute about your own vocation. Perhaps you're a doctor or an accountant, a farmer, electronics technician, a machinist, a skilled professionist of some type. How did you get to be a professional in your business? How long does it take to become an expert in what you do? Could I take a 2 or 3 week crash course and be as proficient as you are? No. So how are you going to become proficient in helicopters? You're going to have to follow our program and become an expert. Next, we're going to take a look at some of the tools that are required to build the Scorpion helicopter. Here are some of the typical hand tools that are required. These are tools that are found in the average home workshop: hammer, hacksaw, wrenches, files, pliers, socket set. Let's discuss a few of them. You'll need a regular hammer, and you'll need a ball-peen hammer. It's also helpful to have a soft hammer such as the plastic mallet hammer you see. This is to pound on parts that you don't want to scratch up. On the hacksaw, there are 2 types of blades that you can buy for the hacksaw. There is a standard hacksaw blade, and there is a high-speed hacksaw blade. I strongly recommend that you buy the high-speed blade. Although the cost of this blade is about twice that of the standard blade, it will last many times as long. In fact, one high-speed blade will probably last for the complete construction of your whole helicopter, whereas if you use the standard blades, you'd probably use 30 to 50 of them. These blades are available at any good hardware store or at Sears. For your wrenches, make sure that you use good quality wrenches. Craftsman, Proto, Snap-on, Williams, something like that. Don't try to use bargain tools like you see advertised in the comic section of your Sunday paper. These tools are very poor quality, they're hard to work with, they're not precision, and they'll destroy your hardware. There are 2 types of files that I recommend. You should have a set of steel cutting files, such as you see on the left, and you should have a set of aluminum cutting files, such as you see on the right. You'll probably want a flat file, a half-round file, and a rat-tail file. There are a number of aluminum parts in the Scorpion helicopter, and you'll find it much easier to file on aluminum with the aluminum files that are made for that purpose. Steel cutting files tend to clog up when cutting on aluminum. Although they're not essential, a socket set will help to speed up assembling nuts and bolts together. There are several precision tools that you'll need for the assembly of your helicopter. A torque wrench for the proper setting of some of the critical nuts and bolts. A dial indicator for checking the concentricity of some of the components. And it's also very useful in setting up the adjustments on the blades later. A vernier caliper which can measure into thousandths of an inch. You'll not need the accuracy of a micrometer, The accuracy of the vernier caliper will be plenty close enough. Also, since there are a variety of sizes of measurements to be made in the Scorpion helicopter, you would need to have a complete set of several sizes of micrometers, both inside and outside, as well as depth gauges. Whereas the single vernier caliper will measure from 0 to 6 inches, inside, outside, and also act as a depth gauge. We also recommend a protractor level, as you see in the upper right-hand corner. This is a level which comes as part of the tri-square machinist square. It's very handy because the bubble can be rotated and the degrees read right on the scale. This is much easier to use than a standard straight level and then trying to calculate the number of degrees. Earlier, you saw that Rotorway does all the heavy machining of the components that you'll receive. The power tools that you'll need will be a simple drill press, a bandsaw, a grinder, and a hand drill. The hand drill is helpful for drilling holes on the ship on location. However, the drill press is easier to use when working on sub-assemblies. It also drills more accurately and it turns at a slower speed, which makes the drilling easier. The bandsaw is very helpful for cutting out your bracket material, and the grinder is used for grinding the brackets down to size. We recommend for welding on the Scorpion helicopter that you use oxygen acetylene. Let's discuss several different methods of joining metal together. First, brazing. Now, brazing is not welding, and brazing is not approved by the FAA, so you cannot use it to put your airframe together. A very popular type of welding nowadays is electric arc welding. However, electric arc welding creates a localized heat and it causes hardening or brittling of the 4130 steel, and it also is not approved by the FAA for aircraft welding, so you cannot use an electric arc welder. You can heliarc, or you can use acetylene gas. Heliarc is a very fine method of welding on aircraft chromoly steel, but it does require expensive equipment and it does require technique. Gas welding, on the other hand, is rather inexpensive to purchase and rather simple to use. It's very forgiving, and we recommend it for the novice welder. If you're afraid of your welding technique, or if you don't know how to weld, we recommend that you go ahead and use the gas process and tack weld all your parts together on your Scorpion. Then when you're all completed, you can have a buddy or you can hire a professional welder to come in and go over all your welds, and he'll cover them. When welding on 4130 chromoly steel, you must be very careful not to let the weld cool too rapidly, or this will cause the metal to become hard and very brittle. Welding should not be done when the ambient temperature is less than 70 degrees. If you do weld when the temperature is lower than that, then you should play the torch off of the weld very slowly to allow the joint to cool slowly. If you weld parts while they're being held in a vise, you should reheat them after they're removed from the vise to allow them to normalize. The vise acts as a heat sink and causes the metal to cool too fast and, again, will cause brittle or hardened parts. If at any time you experience difficulty in drilling a hole through a part that you've welded, or if when you go to bend the part you notice it's hard to bend, you'll know that you have used improper welding techniques and you have hardened the part. You should go back and reheat the part and normalize it before continuing. This hardened part will have a tendency to crack and break later. Throughout the Scorpion aircraft, we use bushings in many areas in the frame to strengthen the frame. You see, if you drill a hole through the frame and then you put a bolt through it and tighten the nut and bolt together, you're going to crumple the tube. So we put a bushing through to strengthen this area. Now here we see several examples of right and wrong bushing installation. On the left we see a bushing which has been put through the frame, but the bushing has been put through at an angle. It's crooked, so the part that will be bolted to the frame will be crooked. It'll also cause a strain on it. In the next example, you see a bushing that has been put through correctly. In the third example, we see a bushing that has been put through correctly. However, look at the bushing right where the head of the bolt is. You notice that the bushing has not been filed flat or perpendicular. When we tighten this nut and bolt, it's going to put a shear force on the head of the bolt and it's going to snap the head right off the bolt. This is not correct. At the extreme right, you'll see a bushing that's been installed through the frame, but you see it only sticks out one side. This is the technique that is used when something has to be bolted flat to the frame. The procedures for making this type of installation will be shown in your step-by-step picture instructions that come with your Scorpion. First, we dimple the flush side of the frame so that when the bushing is put through, we can weld it on both sides. The bushing must be welded on both sides to strengthen it. On the flat side, we must dimple so that the weld can be recessed into the frame area. Here we see depicted several different types of hardware. At the left, under A, is the standard hardware store variety of hardware. This type of hardware is not used in aircraft. It is usually made of rather soft material, not very strong, and is not made very precision. The hardware shown in B through F is aircraft hardware. This hardware is made to very careful specifications. It has the right hardness and the right strength, and it is made to closer precision tolerances. You'll also notice when you examine aircraft hardware that the shank of the bolt is not exactly the same diameter as the threaded area. The threaded area is slightly undersized. The reason for this is to prevent you from adding more threads to the bolt by running a die on it. If you try to run the die down the bolt and cut more threads, you'll probably ruin your die because of the oversized condition of the shank. Also, because of the forces required, you'll cause crystallization of the bolt, and the bolt will be definitely damaged. So don't run more threads on aircraft bolts. You see, bolts work much like rubber bands in holding parts together. If you had a package of papers and you wanted to tie these together with a rubber band, and you put a rubber band around that was very loose, the papers would just all fall apart. In order for the rubber band to hold the papers together, it must be stretched and tight around the papers. The same is true with hardware. A bolt, in order to hold parts together, must be stretched or under tension. If you were to run the nut all the way down on the threads until the nut hit the shoulder part of the bolt, then the nut would be tight, but the parts being held together would not be tight. Now, the FAA has specified that all aircraft hardware have a certain number of threads for a certain size bolt. If the nut is screwed onto the bolt all the way down to the shoulder of the bolt, there'll be a certain number of threads showing, and then the FAA inspector will know that the chances are the bolt is not holding the part together properly. So the FAA inspector does not want to see too many threads showing. At the same time, he must see at least one thread coming through the nut. If you'll examine this aircraft hardware closely, you notice that the nuts have a plastic or nylon insert in them, which is not threaded. And as the nut is screwed onto the bolt, the threads in the bolt will cut threads in this plastic insert. This keeps the nut from vibrating and coming loose. If the nut is not screwed onto the bolt to where at least one thread comes completely through the nylon, then you cannot be assured that all of the nylon surface is gripping the bolt. Now, sometimes we'll have an installation where we do not want the nut and bolt to be tight. We may have two parts bolted together where they have to be able to move in relationship to each other. In this case, we would not use the elastic stop nut, but rather we'd use hardware such as you see in D. This is a cassellated nut. You notice the little cassels on the nut, and you notice a hole drilled through the bolt. With this type of hardware, we can put parts together and tighten the nut up to the proper tightness where it's still slightly loose, and then we put the cotter key through the nut and the bolt, and this keeps the nut from coming loose. Sometimes we'll be putting a bolt into an area where we can't use a nut. For example, when we're going to screw a bolt into a shaft or into a plate. Then we'll use hardware like we see in figure C. Here the bolt will be screwed into the part, and then the safety wire pictured above the bolt will run through the little hole in the head of the bolt and be secured to some point outside the bolt, or if there are several bolts, we may sometimes safety wire from one bolt to another bolt. This will keep the bolts from coming loose. In E and F, we're illustrating some precision hardware. Figure E shows a bolt that is a standard aircraft type bolt. But over in F is the same size bolt, but you notice the shank of the bolt is rather shiny. This is a precision bolt. It has been precision ground to the exact size. Now, although both of these particular bolts shown are 3/8" bolts, The one in the left, under figure E, is nominally 3/8 of an inch in diameter. The one under F is precision, 3/8 of an inch. This type of hardware is used wherever a precision fit is required. And wherever precision hardware is supplied in the Scorpion, make sure that you always replace it with precision hardware. Some examples of machined surfaces. On the left are two parts as received from Rotorway. Notice how nicely they have been machined. On the right are two parts that were returned by a customer. Notice how nicely they've been remachined. See all the niches, the gouges, and the scratches? These will seriously weaken a part. A scratch or a nick in a part will cause a reduction in the life of that part by as much as 10 times. Take care in handling your parts that you do not mistreat them like this. Remember, any nick or scratch is a stress area, and it will develop into a crack. In any fabrication of parts, make sure that you always radius your corners. Square corners act like a scratch, and they will act as a stress point. So make sure that you smoothly radius all corners on all parts. When you're bending brackets, make sure that you don't bend the brackets real sharp. Keep a slight radius in your bends. The radius of the bend should usually be about equal to half the thickness of the material. You may find it helpful to file a little edge off your vise to form these parts, or bend a piece of scrap aluminum to put around the jaws of your vise so you'll have something to form a radius over. If you should inadvertently get a scratch or a nick in a part, then take a fine file or sandpaper and remove the scratch. This will make the part 10 times stronger. Or perhaps I should say, not doing it will make it 10 times weaker. There are several different types of machine fits that are used in a Scorpion helicopter. These are described as press fits, ring fits, slip fits, and loose fits. A press fit is a very tight fit, and it needs an arbor press to put it together. All of the press fits in a Scorpion helicopter have been done for you by Rotorway. A ring fit is a very tight fit, and it could be described as a hand press fit. You do not need an arbor press, but it will be a very close tolerance fit. You will be supplied with some fine sandpaper, and it may be necessary from time to time to take a shaft, for example, and polish it down a little bit with the sandpaper to get the bearing or the part to fit on it properly. Don't use a hammer and force the part on. We will also be furnishing some anti-seize to be used for assembly of these parts. The anti-seize makes it easier to assemble the part and also keeps the part from freezing onto the shaft, so it'll be easy to remove later. A slip fit is a rather loose fit, and the parts will go together very easily. Then lastly, we have what we call a loose fit. This is almost a sloppy fit. Most of the bearings used in a Scorpion helicopter have a locking ring. If you look at the bearing at the lower left, you notice that the hole in the inner race of the bearing appears to be off-center. This is not true. The hole is on center, but the inner race in itself is eccentric. And if you look at the lock ring to the right, you notice that it also has an eccentric surface. When these two units are assembled on the shaft, as you see above, and the locking ring is turned, this eccentric action between the bearing and the locking ring locks the unit to the shaft. You'll notice two holes in the lock ring. One hole has a set screw. Now the set screw is not what holds the assembly together. The assembly is held together by the locking action of the eccentric surfaces. You'll use the second hole in the lock ring with a spanner wrench or a drift pin and a hammer to drive the ring around to securely lock it. Once the ring is locked, you will then set the set screw to keep the ring from coming loose. Whenever you're putting these assemblies together on a rotating shaft, always lock the lock ring in the same direction that the shaft rotates. This way, as the shaft rotates, it tends to self-lock the locking ring. In areas where the shaft does not rotate in one direction but oscillates back and forth, such as in a control, it doesn't matter which way you lock the lock ring, but we suggest that you always treat the lock rings as a nut, turning them clockwise, so that in the future, when you go to disassemble the unit, you'll know to turn it counterclockwise. we're going to show you some of the components of the Scorpion helicopter and how it goes together. You'll see the airframe components as you receive them. You notice that the main section of the airframe has been already jig fitted and tack welded, and alignment is there for you. The tail boom has also been fitted and has been removed for shipping purposes. You will assemble it as follows. Every aircraft has a leveling or reference point to which the whole aircraft is leveled or referenced. In the Scorpion helicopter, the reference points are the 5 square drive mount tubes in the center of the frame. There are 3 that run fore and aft and 2 that run from side to side. Here you'll see the protractor level set on one of the lateral members and on one of the fore and aft members. All degrees should be measured in reference to these points. Make a simple wooden fixture as you see here, and as is described in the instructions that come with the airframe, and establish the degrees called out in the instructions. After you have established these reference points, you may then install the landing gear. You notice a line on the floor drawn down through the center line of the aircraft. This is to assist you in maintaining the alignment of your airframe as you put it together. After you've installed the landing gear, you may install the tail boom. In installing the tail boom, make sure that you keep it straight where it joins the main frame at point A. It is important in installing the tail boom that you maintain the dimensions called out in the instructions at points B and C. This is important so that the kick-up area of the tail boom, behind area C, will have the proper parallelity between the 2 members. They theoretically should be parallel so that as the belts stretch and we tighten the belts and the tail rotor is extended out, there will not be any buying calls between the 2 bearings on the tail rotor shaft. Yet they should be triangulated to give it more rigidity and strength. So we have to have a compromise between being absolutely parallel and being a triangle. And maintaining these 2 dimensions will help you maintain the proper degree or proportion of parallelity. On the right, you'll see the engine mount components as you receive them, and on the left, you'll see this mount when it is fabricated. After you fabricate this unit, you will install it as you see. You'll see the bracket package. We've tried to amalgamate into this one package as much as possible all the brackets used in the Scorpion helicopter. This allows us to most efficiently use the material. We recommend that you go ahead and cut the brackets out with a bandsaw at this time. Now you don't have to cut them out right to the scribe line, but just roughly cut them out, and then you can grind them down to the scribe lines later. Put them back in the box and keep them for safekeeping. I'd like for you to take a look at the second sheet from the bottom. You notice some numbers stamped on this sheet. You're familiar with working with wood. You know the wood has a grain. And if you put any force on the grain of wood, with the grain, the wood will crack. But yet you can put force across the grain, and it becomes very strong. Now the same is true with metal. It has a grain. As it comes out of the mill, it has a grain structure. A roller stamps the numbers on the material as it comes out of the mill, and these indicate the grain direction. So make sure that all of your bends with metal go across the grain. Now all the material supplied by Rotorway has been scribed with the bends across the grain. But if you should lose a bracket or mess one up, and you decided to make another bracket out of some of the scrap material you have, make sure that you lay this bracket out the same way it was originally so that the bends will be across the grain. You see, many times when builders are laying brackets out, they realize that this material is very expensive. In fact, a single sheet is about $10, and so they try to most judiciously lay out the bracket to get the optimum use of the material. But remember, safety is more important than economy. A final word of caution on your brackets. When you're grinding them, we advise that you hold the brackets in your hands while grinding. It is possible in grinding to overheat the material to such a point that it will harden and brittle. But if you hold them with your hands won't tolerate the heat and you won't be able to get them that hot. But if you use a pair of pliers, you won't notice they're getting that hot, and you could overheat them and cause them to get too hard. And again, a reminder that when you make the bends, make sure that you keep a radius in the bends. Also, take a file or sandpaper and remove all the nicks and scratches that you may be putting in these parts while working them in the Scorpion helicopter. We'll see the mechanical components of the helicopter and how they go together. Here we see the lower collective and the secondary drive. The lower collective is on the left and shows the main shaft and the main drive sprocket. Also, you'll notice the little yoke, which is the lower collective mechanism. On the right is the large secondary drive sprocket. The secondary drive is used to reduce the speed of the engine down to the speed of the main rotor. You will notice on these rather intricate and precision parts that all the heavy machining has been done for you. There will be a slight amount of work that you'll have to do to complete these units. For example, on the large sprocket, you'll notice on the outside perimeter there are several holes that have been located and center tapped. You will drill these holes. In the center are 4 more holes which you will drill. They've already been located for you. In the lower center part of the picture is a fork, which is the lower collective mechanism. This is a casting which has already been pre-machined for you. However, you will have to do some filing and dressing up to make the rod ends fit properly. After you have this unit assembled, install it in the ship. When installing this shaft, it's very important that you follow the instructions and install it at the right angles as called out in the instructions. For checking the angle of this shaft, you'll reference it with your protractor level to the square drive mount tubes. Remember, the square drive mount tubes are the reference point for the helicopter. If this shaft is not installed properly, it will seriously affect the high-speed performance of the helicopter. Here we'll see some drawings of the helicopter. Now, we said that the main shaft must be installed properly in order for the ship to fly properly. In Figure A, we see the shaft installed properly, and we see the helicopter is hanging in a level mode. In Figure B, we see the shaft installed improperly. The shaft should be installed on the dotted line, but rather it is installed at an angle to the rear. This would cause the helicopter to hang at an angle. In flight, the control stick would be displaced from its normal position in the fore and aft mode to correct for this. Since we would be flying with the stick displaced from its normal position, it means we would not have as much control power left in that direction, and this would be a hazardous flight condition. In Figure C, we're looking at the ship from a front view, and again we can see that when the main shaft is properly installed, that the ship will hang level in the lateral mode. In Figure D, we again see the shaft installed improperly in the lateral mode. It should be installed on the dotted line, but since it's installed at an angle, it's going to cause the ship to hang laterally in an angle, and we would find ourselves limited in control power in the lateral mode. Not only would having the shaft in improperly cause us to have limited control power in our stick, but it would also cause some hooks joint in the main rotor system, as we will discuss later. We will now install the secondary drive unit. It is important when installing this unit that the small sprocket on the top be at the same height as the large sprocket on the main shaft. We must also take care to see that this shaft is in alignment in both the fore and aft and the lateral mode with the main shaft. This way, we'll not be putting any undue pressure or strain on the chain. If they were not aligned, then either the top or the bottom of the chain would be carrying most of the load, and this would not be a satisfactory condition. The tail rotor components as you will receive them. Here again you will notice that the machining has been done for you. You will notice that the tail rotor blades are completed and the airfoil is established in them. The spars have been installed at the right angle so the tail rotor blades will respond properly. The pivot pins and the pitch horns have been installed and the precision holes drilled locating them on assembly. The tail rotor pulley A is a casting and has been machined for you. The pulley is made of aluminum. In fact, all of the pulleys used in the tail rotor drive system are of aluminum to keep them lightweight. However, aluminum is not a very long-wearing material. In order to allow this material to wear better, it has been hard anodized. Hard anodizing makes aluminum almost as hard as case-hardened steel. You will be drilling a hole through this pulley to locate it on the shaft, and you must use care while drilling this hole that you do not break your bit, because this is a very hard surface. Slider assembly B has also been completely machined for you and assembled. This is the mechanism that controls the pitch on the tail rotor. The tail rotor hub, or bearing container assembly as it is called, C, is a very precision assembly and has been completely machined for you. The tail rotor blades are held into this unit with two snap rings, and it's very important that these snap rings be properly installed, or the centrifugal loads imposed by the tail rotors could cause them to come loose. Take a look at the snap rings. If you look at snap rings very closely, you'll see that one side is rounded and one side is sharp. Snap rings are stamped out of large sheets of steel and then hardened. Because of the stamping process, the die leaves a rounded surface on the top and a sharp edge on the bottom. Anytime you're installing snap rings in a unit or an assembly, make sure that you install the snap rings so that the sharp edge is the edge that will have the thrust against them. For example, in the tail rotor barrel assembly, the sharp edge should be towards the outside of the barrel of the hub. If they were installed with the rounded surface out, then with the centrifugal load against them, it's possible that the snap ring could extrude out of the snap ring groove. We see the tail rotor assembly completed and installed on the ship. The slider mechanism, B, is operated through a mechanism to the foot pedal, and this controls the pitch on the tail rotor blades. The action of the slider B is transferred through the pitch links A to the pitch horns C. Only one of the pitch horns is visible in this photo. The pitch links A are adjustable and are used to adjust the individual pitch of each tail rotor blade. These must be adjusted so that both blades have the same pitch. In this manner, as the slider moves in and out, it will cause the pitch to change equally on both blades. All blades in all helicopters, both the tail rotor and the main rotor, are designed to travel with a tip speed of approximately 400 miles an hour. If you can envision this ship flying through the air now, and the ship is going forward at a rate of 100 miles an hour, we can see that the top blade is traveling forward at 400 miles an hour plus the 100 miles an hour of the aircraft, or 500 miles an hour. At the same instant, the lower blade is traveling 400 miles an hour, but in a rearward direction, so minus 100 miles an hour equals 300 miles an hour. So we can see that there is a 200 mile an hour difference in the speed that these two blades are traveling. Since they both have the same pitch, we will have a 200 mile an hour differential of lift being developed between these two blades. With this tremendous differential of lift forces, something has got to give. And that is why on all helicopters, you will see that there is a free flapping point at point D so that the blades can flap back and forth and equalize or seek their own level. You'll notice that the blades, as depicted here, are not perpendicular to the shaft, but rather that the top blade, which has more lift, is being pulled out, and the lower blade, which has less lift, is receding inward. It is this freedom to flap that takes the strain off of the tail rotor shaft. Also notice on the pitch links A, where they connect to the pitch horns C, that these rod ends will have to oscillate as the tail rotor flaps back and forth as it goes around. It's very important to keep these rod ends properly lubricated, and also to ensure that when the tail rotor flaps to its extreme angles, that the rod ends do not bottom out, putting any strain on them. The tail rotor turns at about 2,500 RPM, and these rod ends are oscillating at that rate. And even if they just barely bottomed out, this slight amount of strain each time it oscillates at 2,500 RPM would eventually cause a fatigue in the rod end. We'll take a look at some of the forces that are existent in the tail rotor system. These same forces are existent in the main rotor system, and we mentioned them briefly when we were talking about the main shaft a little earlier. Although the pivoting action, or the universal, occurs right at the juncture of the shaft with the hub, It'll be easier to illustrate and see this if we drop the universal joint down on the shaft as shown at the X. Let's take a look at the figure on the left. The X represents the universal joint, and you'll notice that the lower portion is called the driver, and the upper portion is called the driven. There are two types of universal joints that can be used: the constant velocity joint and the Hooke's joint, which was named after Mr. Hooke, who described the physical laws and properties of this type of a joint. A constant velocity joint has a constant velocity at all times. However, this type of a joint will not stand high thrust loads, and since the tail rotor will be developing as much as 65 pounds of thrust, it would take a very large and very heavy joint to use a constant velocity joint in this location. And in the main rotor system, which has to support the whole weight of the helicopter, you can see it would take an extremely large and heavy joint. Therefore, we're limited to using the Hooke's type joint in these applications. The Hooke's joint is the type of a joint you find in the universal in the drive shaft of your car. It will withstand high torque loads as well as high thrust loads, but it does have a disadvantage. When the driver and the driven are in line with each other or parallel, as you see in the figure on the left, if the driver is going at a constant RPM and a constant velocity, the driven will also go at a constant RPM and a constant velocity. However, if we put the driver and the driven off axis, as you see in the picture to the right, although the driver will still turn at the same RPM and at a constant velocity, we'll observe that the driven element will turn at the same RPM, but it will not turn at the same constant velocity. Because of the action of the Hooke's joint, twice each revolution, the driven element will try to increase and decrease in velocity, turning the same number of RPM, but not turning at a constant velocity within each RPM. Now, if you can imagine this tail rotor spinning around about 2,500 RPM, you can imagine the tremendous centrifugal loads that are generated. This is acting like a large flywheel, and this flywheel is not going to increase and decrease twice in velocity each time this tail rotor goes around. Something has to give. In a normal helicopter where they have a gearbox at the rear and a drive shaft driving the gearbox, you can see that there are tremendous loads imposed in the gearbox and in this drive shaft. This drive shaft is having to flex twice each revolution to absorb this Hooke's joint effect. This is putting some tremendous forces in the tail rotor drive shaft and in the gearbox. The Scorpion does not use a drive shaft and a gearbox. Instead, we use a V-belt drive. These V-belts, being made of a rubber compound, are able to absorb all of this Hooke's joint action, and therefore we have the much greater reliability in the Scorpion drive system than is found in the conventional helicopter. It is important in this drive that you keep the belts properly aligned. You'll notice in the tail rotor pulley A that this pulley is properly aligned and the belt is entering and exiting the pulley properly. It is within the sheaves of the pulley. But look at the vertical pulley B. You'll notice that this pulley is not properly installed. It's cocked at an angle, and you'll see that the belt is rubbing on the sides of the pulley as it enters and leaves the pulley. This will cause undue wear on the belt. It'll also cause undue wear on the pulley, wearing through that hard anodized surface prematurely. Once you wear through the hard anodized surface, the soft aluminum inside would wear very fast. Make sure while installing these pulleys that they are properly installed so that the belt alignment is correct. We will see the controls of the Scorpion helicopter. In the background are the components as you receive them, and in the foreground the controls as they will appear after you have assembled them. The Scorpion comes with single controls, but is designed with dual controls which are available as an optional accessory. There are 4 basic controls in a helicopter. On the left you see the cyclic control. In the center you see the collective and throttle control. On the right you see the foot pedal or tail rotor control. This control is shown in the dual configuration. The cyclic control controls the main rotor system. It controls the direction in which we tip the main rotor system and the amount which we tip it. The direction in which we tip the rotor system will determine the direction in which the helicopter will fly, and the amount that we tip it will determine how fast it will fly in that direction. The collective system, collectively or together, controls the pitch on each of the main rotor blades. This will control the amount of lift or thrust that the main rotor system will generate. The rotor systems in all helicopters will always turn at a constant designed RPM. Therefore, to change the lift, we will change the pitch on the blades. Even though the blades are always turning at a constant RPM, whenever we change the pitch or the lift on the blades, we must change our throttle setting. You see, if you were driving your car down the freeway at an honest 55 miles an hour, and I know you're a nice law-abiding citizen, and you came to a hill and you wanted to maintain that 55 miles an hour, you'd have to depress the gas pedal some. And when you went down the hill on the other side, you'd have to let up on the gas some. Well, the same is true with the helicopter. To keep those rotor blades turning at a constant RPM, if we decide to pull up on the collective and to start climbing, we'll have to add some throttle. Conversely, if we wish to descend, we'd have to reduce the throttle somewhat. At the end of the cyclic handle, you'll see a motorcycle type throttle grip. This is used to regulate or to maintain your RPM. On the right, you'll see the foot pedal controls. These control the pitch on the tail rotor blades. Since the main rotors are being turned by the engine and a lot of torque is being developed, and as the blades turn one direction, the body of the helicopter will want to turn in the other direction, the tail rotor generates a counter torque to hold the heading of the helicopter constant. For those of you that are familiar with aircraft, this would be called the yaw control. Here we see the cyclic control installed. Although the Scorpion comes with single controls, here you will see the dual controls installed so you can see how they will look. It's very important when installing the controls that you follow the instructions very carefully to get the right number of degrees of movement for the control. In other words, make sure the operating parameters are correct. This is to ensure that the ship will have the proper sensitivity of control. For example, the instructions call for this control to have a side-to-side motion of 52 degrees through its arc. Let's say that you had adjusted the control so it only had 10 degrees of travel. Do you see how touchy and sensitive it would be to control it? On the other hand, if you set it up for more than 52 degrees, you'd not have enough space between your legs to run the control from one extreme to the other, and you might find yourself under some conditions not having enough control. So setting the control up to the proper parameters is very important in order to have the proper controllability or sensitivity of the ship. The controls in the Scorpion helicopter consist of control rods and actuating arms. Let's look at figure 1. Here we see a shaft marked S with a control arm mounted to it. And to the control arm is mounted the control rod marked CR. If the arm is mounted 90 degrees to the control rod, and if the shaft is rotated from position A to position B, we'll see that the control rod at the upper end will move from position A' to B'. But if we do not mount the arm 90 degrees, but rather, as in figure 2, the arm is mounted down at an angle, now we see as we rotate the shaft from position A to position B, the control rod will move from position A' to B'. You'll see that the rod moves a lesser amount for the same number of degrees of rotation of the control shaft S. We can see then that if we do not mount the arm properly, we'll not have the proper amount of travel of the control rod for the proper travel of the control shaft. It's important, therefore, that we watch the mounting of all of our arms, that they are correct, so that we'll have the proper ratio of travel between a control handle and a part that handle will move. Here we see an example of this. Control arm A is mounted 90 degrees to control rod B. When the cyclic handle D is moved from side to side, control arm A will go equally above and below center line, causing maximum travel of control rod B. You will also notice that walking beam C is mounted 90 degrees to its control rods, and as the cyclic handle D is moved from side to side, walking beam C will move equally above and below center line. The proper mounting of these control arms should be maintained throughout the control system of the Scorpion helicopter. There are, however, two arms that are not mounted in this manner. The collective control arm E and the foot pedal control arm F are not mounted 90 degrees because of certain design criteria. Here we see the collective and throttle assembly installed. When you install this unit, be sure to maintain a clearance between the throttle A and the frame B so that you do not pinch your fingers when you put the collective all the way down. If you intend to use the doors, which are an optional accessory, make sure the control is not mounted too far out, or when you pull the collective all the way up, the throttle would hit the doors. The collective mechanism consists of control stick C, which operates control shaft D, which operates the control rod E. The throttle mechanism consists of the throttle handle A, which operates the throttle rod F, which in turn operates the throttles on the carburetors. In the collective throttle mechanism, there are three sets of roller bearing assemblies. To the throttle bracket A is welded a round piece of tubing, which is the bearing container. Into the ends of this container are pressed the bearing retainers C, and bearings D are pressed into these retainers. The throttle shaft B goes through these bearings, and the control arms E are pinned on each end. The bearings D are roller bearings, and it is a characteristic of roller bearings that if they are not in alignment, as the shaft is rotated inside them, the shaft will tend to screw in and out, or back and forth. So you can see if you had this out of alignment condition, the shaft B would try to screw back and forth and bind up on control arms E. As you weld bracket A to the round bearing container, the heat of the welding action will cause the round tube to take a slight bow, and this will cause the bearings to be out of alignment. Therefore, after you weld the bracket A to the round bearing container, it will be necessary to heat the other side of the round bearing container to straighten it back out. Make sure that you take care to get this assembly straight so that the needle bearings will be traveling in line and not cause any binding. Use this procedure in all of these needle bearings in the throttle collective mechanism. We see the tail rotor directional control installed. Although the Scorpion comes with single controls, as shown on the left, the dual controls are also shown installed to the right. Be sure in rigging this control that you have the proper number of degrees of pedal travel as called out in the instructions. This will ensure that you have the proper sensitivity of control. In this slide, you will see again control arm F. This is one of the two arms that is not mounted 90 degrees to its control rod, or in this case, its control cable. If you look at the control cable at area G, you'll notice that the end of the cable has a ferrule. This ferrule has a freedom of motion in it to allow for any misalignment of the cable. As the arm goes through its arc of travel, the cable will have to flex up and down. Be sure you do not exceed the free flexing of this ferrule, or you could damage the cable. Here we see the swash plate and the hub assembly as you will receive them. The cyclic handle controls the swash plate, which in turn controls the rotor hub, which controls the attitude of the rotor system. This, as we discussed earlier, will control the direction in which the ship will fly and the speed at which it will fly in that direction. Here we see the swash plate installed, and we see the control rods connected to it. We can see the rods going down to the cyclic handle, and we can see the rod which is going to go up to the hub. It is connected at the swash plate, but not yet connected at the hub which is not yet installed. If you have properly rigged your cyclic handle and you have all your control arms mounted properly at 90 degrees, when the cyclic handle goes through its proper number of degrees of travel, the swash plate will go through its proper degrees of travel. You'll notice as you're rigging this control up that the swash plate is not designed to have the same number of degrees of travel to the left and to the right. Here we see a top view of the helicopter. The main blades are turning in a clockwise direction, and the torque causing them to turn in this direction is creating a counter torque causing the body of the helicopter to want to turn in a counterclockwise direction. To compensate for this torque that is causing the body of the helicopter to want to turn in a counterclockwise direction, we mount a tail rotor on the end of the ship that is pulling, as you see, in C. This will keep the helicopter from spinning around, or as we say in aircraft terminology, it is the yaw correction. If we wish to make a turn to the right, we apply more force at C, and this will cause the helicopter to turn in a clockwise direction. If we wish to turn counterclockwise or to the left, we reduce the torque on the foot pedals or the tail rotor, and the torque that's applied to the body will cause the ship to turn to the left. You will notice by looking at the blade that there are two blades, and they are both trying to turn in a clockwise direction, about a central point in the middle, the main shaft. This is called a couple torque, and this torque is trying to cause the body of the helicopter to turn in a counterclockwise direction, about the same point. Again, a couple torque. The tail rotor, which is compensating for this turning motion, is a single torque, or called a moment torque. We can see then that the tail rotor torque, which is in a single direction, C, is trying to compensate for a rotating torque of the main rotor blades and the body, A and B. Although this tangent torque C is pulling in a direction, it will keep the body from spinning around, but it will cause the helicopter, as we try to hover, to want to drift in that direction. That is, the helicopter will want to drift to its left. This is called the translating tendency of the tail rotor. To compensate for this translating tendency, we must always take the cyclic stick and move it to the right and fly the helicopter as though we were flying to the right in order to maintain a position over the ground. For this reason, the swash plate must have more travel to the right than it has to the left. You will have a close-up view of the hub as you will receive it. Take note of surfaces A. These surfaces are very precision machined with a precise angle on them. Do not do any filing or work on these surfaces that would upset them. Surface B is rough finished, and you may do some filing on these surfaces. You may have to dress these surfaces down in order for the blades to fit on properly. There should be a clearance of about 30 to 50 thousandths from the bearings in the rotor blade assembly to this surface. Less than 30 thousandths might cause some binding. More than 50 thousandths would put undue stress on the pitch pins. There are 7 holes that you'll have to drill in this unit. There are 4 holes down the center line marked with the X, which will be drilled and tapped for set screws to hold the pitch pins in place. The 2 holes on the left for mounting the collective stanchion, and the 1 hole on the right for mounting the counterweight. You will notice in the center of the hub that the riser blocks and the main universal are already assembled as you receive them. These units are very precision aligned. Although you'll have to remove these units to do the work that we just talked about on the hub, make sure that you take it apart very carefully and observe the position of all the shims and the parts so you can put it back together in exactly the same manner. The pitch pins in the hub must be exactly in alignment with the hole through the middle of the universal. This will ensure that the blades are mounted exactly on the center of the main shaft. You can imagine if this universal were displaced even a few thousandths, the tremendous eccentric and the vibrating action we'd get when the blades started spinning at full RPM. You'll see the riser blocks and the universal removed. Look carefully at the holes in the hub for the pins at position A and B. You'll notice that the holes at point A are closer to the top surface of the hub plate than they are at pin B. This will cause the blades to be put on the hub at a slight angle. In Figure 1, we show the rotor blades A and B attached to the rotor shaft. We see that blade A is equal in length to blade B. If we were to plot the center of mass for these blades AB, we would find that the center of mass, CM, would fall right on the dot. This shows the blade system in a hover condition. Now, if we wish to fly to the right, we would flap the blades to the right as we see in Figure 2. We could draw some vectors of this blade system, and we would see that we still have lift, but we have also a force pulling the ship to the right. You will also notice that blades A and B are still equal in length, or equidistant from the center point of rotation. Now, this would be fine if helicopter blades worked this way, but they don't. You see, helicopter blades have to be very lightweight, and they're quite limber. If we were to have a helicopter sitting on the ground in a static condition, and I got on the one end of one blade, and you got on the other end at the other blade, and we tried to pick the helicopter up, we would not lift the helicopter off the ground. We would merely succeed in collapsing the blades like an umbrella in a windstorm. You see, we have to rely upon the centrifugal force of the blades turning to keep them out rigid and straight. Now, as we start to put lift on the blades with the collective handle by putting more pitch into the blades will start to develop a lift. But the blades will not immediately lift the helicopter off the ground. Instead, the blades will start to climb, they'll start to lift, they'll start a cone, such as we see in Figure 3. When the coning or bending moments equal the centrifugal forces, then the helicopter will start to lift off the ground. This is the reason the helicopter rotor systems must always turn at a constant RPM. They must turn fast enough so that they'll generate enough centrifugal force to maintain the proper amount of rigidity. Yet we don't want to turn them too fast, or we generate too much centrifugal force and we would exceed the design criteria of the hub. Another factor to be considered in the design of the speed of a rotor system is that since the blades are rather narrow in chord, they must turn very fast through the air in order for this small airfoil to develop sufficient lift. Yet if we turn them too fast, the tips of the rotor blades could exceed the speed of sound and we'd have a sonic boom, and that would not be a pleasant experience. Therefore, all rotor systems must be designed with a tip speed that will develop the proper amount of centrifugal forces to make the blades rigid, go fast enough to develop lift, yet at the same time not develop too much centrifugal force, and not approach the speed of sound. All helicopters operate with their blades with a tip speed of approximately 400 miles an hour. This is true both of the main rotor and the tail rotor. This is why in a small helicopter, such as the Scorpion with the short blades, we turn at 500 RPM to generate these forces, and a larger helicopter with longer blades would turn at a lower RPM so that the same forces would be generated. In Figure 3, we see this coning action on the blades, exaggerated here for clarity. We see that the center of mass is still equidistant from blade A to blade B, right over the point of rotation. However, vertically, we see that the center of mass has been displaced to an imaginary point outside of the blades as shown on the dotted line. The key point here, however, is that blade A and blade B are still equidistant from the point of rotation. If we now flap the blades, though, to fly to the right, as we see in Figure 4, we see that blade B comes down and blade A comes up, and we see that the center of mass now shifts off of the point of rotation. And we see that blade B has become long in relationship to the main shaft or the point of rotation, and blade A has become short in relationship to the point of rotation. Now, we know from the laws of physics that as the mass becomes greater, the velocity decreases, and as the mass becomes shorter, the velocity increases. This is evidenced by the pendulum on a clock. Here we now have two blades attached to a main shaft, 180 degrees apart, and rotating around. But as they rotate, blade B, which has become longer, wants to slow down, and blade A, which has become shorter, wants to speed up, and they no longer want to maintain this 180-degree relationship. This means the blades will have to bend as they go around. And of course we know that the blades could not go around very many revolutions with them bending back and forth before they would break off. Something must be done to take care of this. There are three approaches. One is the rigid rotor system. In this system, the rotors are fastened to the main rotor shaft, 180 degrees apart, but the blades are made of some exotic material such as titanium and just allowed to bend. They still don't last too long and have to be replaced quite regularly. Being made of exotic materials, they're very expensive, so we can see that this is not the type of a system to be used by the general public. This system is only really practical for the military. The second way to correct for this situation is to use the fully articulated rotor system. In this system, the blades are pivoted so that they can pivot back and forth as they go around. This is a very good solution, however it does have a drawback. If the helicopter is bounced on the ground during takeoff or landing, it could cause the blades to go out of phase, and then we would really have a vibration. And in fact, the helicopter would probably self-destruct within about 3 to 3.5 seconds. We did not feel that this would be the proper system to be used in a helicopter designed to be built and operated by the novice. Therefore, we used the third system, the semi-rigid underslung. In Figure 5, you see the semi-rigid underslung system. You'll notice that the hub is mounted on a pivot point on the top of the rotor shaft, but the blades are connected to the hub down below this pivot point. You notice as the blades are coned that the center of mass, this imaginary center of mass, falls on the pivot point on the shaft. You'll notice that blade A and blade B in the hover condition are equidistant from the point of rotation. As we flap the blades to the right in Figure 6, you'll notice that as the hub pivots on its pivot point, blade A lengthens and moves out, and blade B shortens by pulling in, so that we still have blade A and blade B equidistant from the point of rotation. It can be seen that in the design of the rotor hub system, the amount of this underslinging must be designed so it will be right on the center of mass with the blades coned as they will be in flight. Since the coning angle of the blades will be determined by the speed at which the blades are turning and the centrifugal forces generated, it's very important that we maintain the rotor RPM at the proper RPM so that the undersling will always be correct. Too low an RPM would generate less centrifugal forces and we'd have more coning, and our underslinging would not be correct for that amount of coning angle. Conversely, too much RPM would generate too much centrifugal force and our underslinging would be too great for the coning angle. Also, too much RPM would generate too much centrifugal forces on the hub. Another factor is the weight in the helicopter. If we tried to carry too much weight, this would cause the blades to cone more also, and our underslinging would not be correct. People often ask, can you put in a larger engine and carry more weight? You can see, though, that horsepower is not the determining factor. The determining factor of the weight that a helicopter will carry is the amount of underslinging that is designed into the hub system and the amount of coning angle the blades are designed to carry. For this reason, a helicopter should always carry a weight within the minimum and maximum specifications as called out by the manufacturer. We can see then that in any helicopter we must run the rotor system at the proper RPM and we must carry approximately the correct weight. Running the rotor system as much as 50 RPM low will cause the coning angle to double, and when the coning angle doubles, the wear on the blades will be increased 4 times, or we could say will shorten the life of the blades by 4 times. It's recommended that the rotor RPM be maintained within a fairly close tolerance, approximately plus or minus 10 RPM. This may sound difficult to do, but it really isn't. When you drive your car down the highway, you're able to maintain 55 miles an hour without any problem. You don't have to constantly keep your eye glued on the speedometer. Occasionally you just glance at the speedometer, make sure that your reference isn't changing. The same is true in the helicopter. You'll develop a feel for the rotor blade. You hear them going around like that. and you'll develop a sense for it. You'll very easily be able to tell a change of 4 or 5 RPM. Occasionally you'll glance at the rotor tack to make sure that your reference hasn't shifted on you. In any aircraft, the aircraft will be rated for a certain amount of total weight it can carry. But you just can't put that weight any place in the aircraft. It must be properly distributed. You can't put it all in the front seat or all in the rear seat or all in the baggage compartment. This is called proper weight and balance. In a fixed-wing aircraft, because we have a large wing out front and an elevator towards the rear, we have a fairly stable condition, and the weight and balance can be distributed within plus or minus 12 to 14 inches. But in a helicopter, since it hangs from a single pivot point, as we see in Figure A, a slight change in weight and balance can cause the ship to hang nose down or tail down. We can see then that in a helicopter, the distribution of the weight is very critical. In Figure A, we see the weight properly distributed and the helicopter is hanging level. In Figure B, we see that the weight is distributed too much towards the front of the aircraft, and we see the helicopter hanging nose down. Look at the juncture of the main shaft with the rotor blades. Look at the acute angle here. If you will review slide 48 and the discussion at that time, you'll see that this causes quite a bit of Hooke's joint. This Hooke's joint will have to be absorbed by the main shaft and the secondary drive, or our transmission system. This is why we use a belt drive in the Scorpion helicopter. Most helicopters use a gearbox, but can you see all of the forces that be applied upon the gears of a transmission? That's why the transmissions don't last too long in a helicopter. But the V-belt drive of the Scorpion is able to absorb all of this Hooke's joint effect. However, we do want to try to minimize this Hooke's joint as much as possible because it does cause forces in our hub system, the main shaft, the large sprocket, and the drive chain. The more we can reduce these forces, the longer all the components will last. Figure C shows these same conditions in a fore and aft mode. Here we're looking at the ship head-on, and we can see that the weight and balance is distributed properly and the ship is hanging level. Figure D shows a helicopter improperly weight and balanced in the lateral mode. Now we can see the weight is to one side and the helicopter is hanging off to one side, again causing a Hooke's joint in the main rotor system. We see the hub unit finished and installed on the helicopter. Here we can see the cyclic rod A connected from the swash plate to the rotor hub. This rod, connected to the swash plate, which in turn is connected to the cyclic handle, controls the attitude of the main rotor system. We also see the collective control cable, B, which controls collectively the pitch on both blades. We see the body components as you receive them. Wow, you say, that looks like a real jigsaw puzzle. But don't panic, it's not that difficult a job. It's a good Saturday morning project to put this back together. If you're familiar with working with fiberglass, you'll have no problem, but even if you're not familiar with fiberglass, the step-by-step instructions shown down in the lower left-hand corner of the picture, next to the body top, will tell you step-by-step how to assemble this unit. You'll see the simple procedure for putting the body together. Then with a little body putty at the joints, a little sanding, a little paint job, you'll have the body all completed. When you install the body on the ship, make sure you use a protractor level and get the windscreen at the right angle as called out in the instructions to the main shaft. It's important in installing the body that we maintain this proper windscreen angle so that we have the proper aerodynamics of the body. We see a condition depicted that is common in most helicopters. We're looking down on the top and we see the blades rotating in a clockwise direction. Now the blade tips are traveling at 400 miles an hour. Let's assume that the helicopter is traveling forward at 100 miles an hour. Now at this time we can see the blade that is moving forward is traveling 400 plus 100 miles an hour, or 500 miles an hour. And the other blade, which is traveling to the rear, is traveling 400 miles an hour minus 100 miles an hour, or 300 miles an hour. Now we have a 200 mile an hour differential of lift between the two blades. We had the same condition in the tail rotor, remember? In the tail rotor, we allowed the blades to just freely flap and find their own center to correct for this differential of lift. But we can't do this with the main blades, because if the blades flapped, then the helicopter would start flying in that direction. So we must have a mechanism in the hub that as the blades come around, the blade that is going forward will decrease in pitch, lowering its lift, and the blade that is going to the rear must increase in pitch to increase its lift. In this manner, we maintain equality of lift on both blades at various airspeeds. However, as the airspeed gets greater and greater, the pitch on the retreating blade, the one that's going to the rear of the ship, keeps getting more and more acute, until finally that pitch becomes so acute that the airflow over the blade becomes disturbed, and then we start losing the lift on that blade. This is called receding blade stall. It would at first appear that this would cause the helicopter to want to roll over to the side. But since the rotor system acts as a large gyroscope, and gyroscopes always react 90 degrees to the force put into them, in reality, the tail of the ship would start to roll down, or the nose would pitch up. At first, it would seem the corrective action for this would be to push the stick forward and push the nose back down. But remember, as we push the stick forward, we get more airspeed, and it was the high airspeed that caused this condition in the first place. On the other hand, if we pull the stick back, this will pull the nose up. So we have a rather difficult situation. This is a condition called receding blade stall, and helicopter pilots do not like to get in this condition. You see, a fixed-wing airplane stalls at low speed, but a helicopter stalls at high speed. In the Scorpion helicopter, as we go faster, there will be a wind pressure generated against the windscreen A. This will cause the nose to want to tuck down B. To compensate for this tucking action, we have a trim fin at C. As we go faster and faster, more force will be generated on the trim fin, causing the tail to want to tuck down. But gyroscopically, this force will proceed 90 degrees later, and the ship will have a tendency to want to roll over to the left. So as we go faster and faster, we will find the cyclic stick wanting to migrate over to the right to compensate for this roll. When we reach some maximum speed, we'll find that the cyclic stick is all the way to the right, and we'll realize that we cannot go any faster because we can no longer compensate for any further roll of the ship. And we will either level off at that speed or we'll slow down. This is called profile drag, and you can see that it is much easier to recover from profile drag than it is from receding blade stall. You see a close-up of this horizontal stabilizer trim fin, and it's very important that you use your protractor level and get it in at the right angle so that it will properly compensate for the profile drag on the windscreen. We see a triangular framework on the rear of the helicopter, and this is called the tail rotor skid. It is to protect the tail rotor and keep it from hitting the ground if we should approach for a landing in a real tail-down condition. It is also the mounting point for the vertical trim fin, which gives us stability in forward flight. This shows the main rotor system as you receive it. This is a very critical unit, and all of the critical assembly is done as you receive it. There'll be a slight amount of work you will have to do to complete this assembly. Now that you know everything there is to be known about helicopters, and you're a helicopter expert, or, well, almost, at least you're well on your way towards it, let's take a quick review in the next 15 slides and see the Scorpion put together. We see the airframe blocked up and leveled. We see the landing gear installed. The tail boom installed. We install the lower collective, the main shaft, get it properly angled. We install the secondary and align it to the main shaft. we install the tail rotor and the tail rotor drive system. Install the controls. Install the swash plate. Put on the hub, connect it. Install the engine. The radiator and the fuel system. Put on the cabin and maintain the windscreen angle. Install the blades. Now we'll make a few simple rigging adjustments on the ship. We're ready to fly. Can you think of anything more exciting and more exhilarating? This is the way to fly. The helicopter gives you the freedom of the eagle. This is the closest thing to pure personal flight. You become a part of the machine becomes a part of you, and you feel this freedom of flight in 362 different directions, any point of the compass as well as up and down. Don't you want to start your Scorpion today? Rotorway wants to be in touch with each one of its customers. We want to meet you personally before you start. And for this reason, we ask that you contact us personally either by phone call or by an appointment in person here at Rotorway or attend one of our seminars. We'd like to meet you, get to talk to you, get to know you. Contact the Rotorway Sales Department and find out how you too can have your own personal helicopter.